been a great pleasure to have André Joyal visiting for the last 2 weeks. We had some nice discussions, and I'm especially grateful that he agreed to give this talk here for us. André is, of course, one of the prime movers in the development of topos theory and has been for several decades now. Not to mention his enormous influence on category theory in general, categorical logic in particular. And so to get his perspective on the development and history of topos theory is especially valuable. Pleasure to have him. And the title of the talk, if I'm not mistaken, is 3 Mutations of Topos Theory.
Thank you. Thank you, Steve. It's really a pleasure to visit Carnegie Mellon and visit the department and to discuss with you and your colleagues and students. And, it's a fantastic place for category theory, logic, and type theory. Computer science, I suppose.
I've heard
philosophy. They do philosophy, of course. Philosophy of science. Yes, I have chosen the subject is 3 mutations of topos theory because I'm actually writing a paper on topos theory for the proceeding of a conference that was held a couple of years ago at the Institute for Henri Poincaré, organized by Mathieu Anel, who is here. Mathieu will be speaking tomorrow about infinity topos, a new aspect of infinity topos, and I hope you will be able to attend this talk because it will contain things that I will not discuss in my talk. Yeah, I've been practicing topos theory almost all my mathematical life, and I felt that I sort of knew what it is, but when I sat down to write a paper explaining what it is, I had a lot of difficulties of various kinds. And I started to try to organize the subject, at least for myself, and maybe this talk would be precisely an output of this thinking. Yeah, 3 mutations. The 3 mutations you have at the origin you have Grothendieck toposes. You have the notions of Grothendieck topos introduced by Grothendieck in the late 50, maybe 58 or 57. I do not know exactly when. And developed in SGA, Séminaire de Géométrie Algébrique, during the early 60s by Grothendieck, his collaborators and students. So this was, let me write just a date, approximate date, 1960, around 1960. And then you had, I would say, a first mutation, which was the notions of elementary topos. Introduced around 1969 by Lorvier and Cierne. It is quite, on the face of it, I mean, the notions of elementary topos is quite different in some sense than the notions of Grothendieck topos. And it's not even clear that it should be called a topos, but it was called a topos from the very start. And so we are used to call that a topos, but I will discuss that a bit later. So this is the first mutation. And the second mutation is the notion of higher topos. introduced around maybe 1998, something like this, by Charles Reck. Maybe writing his name, Charles. In a note on his web, this was not even published, but he just wrote down some notes on something that he had called a model topos in reference to model categories of Pudding. And the notions was soon applied to derive the creations of derived algebraic geometry by algebraic geometers, Bertrand Cohen, Pizzolti, and also by Jacob Lurie, who developed it systematically. So you may be aware of the book by Jacob Lurie called Higher Topos Theory, published as in a Princeton lecture note. And then, so this is the second mutation. And the third mutation, which is now I would say emerging, because it is sometimes called higher elementary topos. And the notion is not yet completely defined, but there are discussions about it. There is, for example, on the web, you can find by Mike Schulman a blog post on the N category cafe, where he proposed the notion of higher elementary topos. And the interesting things about this notion is that it's a kind of synthesis. I mean, it's inspired by, of course, the elementary topos here. It's inspired by that. But it's also inspired by the homotopy interpretation of type theory that was discovered by Steve Abodi, Michael Warren, and Vladimir Vygotsky about 10 years ago. Because this is something I did not say, but I guess everybody knows that there is a connection between the notions of elementary topos and logic. This was discovered very early on by Lauvier and Tierney. The logic here is intuitionistic, so there is this arrow here is about a sort of logical interpretation of what a Grothendieck topos is. And there is a new logical interpretation of what a higher topos is, which started with the homotopy interpretation of type theory by Steve and Marco and Vladimir. So this is what I would like to talk about. I would like to sort of come back to the original notions of Grothendieck topos and discuss the original notion and discuss how the other notions have emerged from it. And maybe I should say that there are more than 3 mutations, because with the notions of higher topos, actually, you have a whole sequence. There is a notion of 0 topos, and then the notions of 1 topos, of 2 topos, and eventually the so-called infinity topos. And the 1 topos are in fact the Grothendieck topos. And the 0 topos are what we call a locale. And many of the things that I would like to discuss are already present in the theory of locale. And so I will start by presenting some aspect of the theory of locale and introduce maybe some new terminology, and then move up to one-topos and possibly eventually infinity topos. So what is a locale? The notion of locale apparently was first introduced by von Neumann. Maybe in the late 40s, I'm not sure the dates about that. But, it may have been introduced independently by Charles Erasmus. And what the idea of von Neumann? The idea is that when you look at topological space, there is, instead of concentrating on the set of points of a topological space, you may very well consider that the basic constituent of a topological space are not the points equipped with the topology, but they are the open subset of the topological space. So let me write OX for the set of open subset of X. And for some reason, I mean, von Neumann was interested in operator algebra. Everybody knows von Neumann algebra and etc. Very often in the theory of operator algebra, you first start with an algebraic system. Maybe, well, it could be a C-star algebra. Von Neumann did not invent C-star algebra, but Gelfand. And from the algebra, you want to extract a space. But what you have are not the points of the space. You first maybe construct something like the set of open subset of that space that you would like to construct. The open subset comes first, and the points come after. So, but the idea of von Neumann was to formalize the algebra of open subset of space in order to describe this abstract topology, which could be called formal topology. So OX has union. You can take the union of open subset, let's say AI, arbitrary union, it is closed under union. And you can take a finite intersection. The intersection of two open is open. So there are essentially two basic operations on the set of open subset of X, union and finite intersection. And these two operations are related by there's a distributivity law, which is that if you intersect a union, let me write the distributivity law is that the intersection union is union of the intersection AI. That's a distributivity law which is valid among the subset, the power set. If you look at the power set of X, OX is a subset of the power set of X. This distributivity law is valid in PX, but since OX is closed under arbitrary union and finite intersection, the law is inherited by OX itself. So this is the basic idea of von Neumann. I'm going to make an abstraction of this and define a few notions. First, definition. Possède partially of a set, let's say L is called a soup lattice. If every subset S in L, soup S, or we can use this notation, which is very handy, a bit like a union for X in S, the element of X. Okay. So I recall this is defined to be the least upper bound. Okay. Now we will need also the notion of morphism between soup lattices. So if you have two soup lattices, L1 and L2, you say that a map from L1 to L2 is a morphism if it preserves a morphism of soup lattices. If it preserves supremum. So if you take the supremum of a family of elements, then it would be Q of okay. So there is a category of soup lattices which I'm going to write S U P, and I will underline it to say that this is a category. So you have the category where the object are soup lattices and the morphism are soup preserving maps. Okay, now I'm going to use this notion to define the formal notions of the topological space introduced by von Neumann.
Is there a reason why it only preserves the suprema, not the whole relation? So I guess I was anticipating that it would just be preserve the whole relation and get the subs from that. But so the way it's defined, it only preserves the suprema, right? Why?
Then it does preserve the
You're going to see it.
They're equivalent.
You're going to let him go.
Yeah, maybe a remark which is important in some sense because it's the first instance of a phenomena. A remark. A soup lattice is also an nth lattice. Although we did not put this in, it is true. In other words, if you have L, a soup lattice, and a subset of L, then the infimum of S can be defined to be constructed as the supremum of all the lower bounds of S. Just check that this is this case. So a soup lattice is also an nth lattice, and this is why people often call a soup lattice a complete lattice, because it has both the infimum and the supremum. However, morphisms of soup lattice that preserve supremum does not mean to preserve the infimum. This is an interesting phenomenon. We introduce a certain structure, suprema, and notions of morphism, and then we discover that the structure, we can define extra operations that are not preserved by the morphism. Now the fact that the operations are not preserved by the morphism means that these operations are not natural, in the sense of natural operation of category theory. Maybe they are natural from the point of view, some other sense of, but from a point of view of category theory, they are not exactly a natural operation on a structure should be preserved by the morphism. We have chosen the morphism corresponding to the suprema, but these morphisms do not preserve these operations. Therefore, these operations are not natural, but they are very useful. Okay? So how should we call them? I have been suggesting various names for these extra operations that are there, that are not natural from the strict point of categorical point of view, but which can be defined. I'm not sure I should. I thought that it could be called meta operation, but maybe I don't know if you would accept this idea. They are sort of operations a bit from the outside of the structure. You have the intrinsic operation of the structure defined by suprema, and then you have these other operations that are maybe, let's call them extra operations. Okay, not to be too fancy. Okay, so let's call them extra operations. These extra operations give you more structure on the sublattice, and they give you a sort of superstructure. They come and they give you a superstructure that are very useful to study sublattices, but okay, I will give you more examples of that. Okay, not preserved by morphism of sublattices. Okay. Now I can define what a frame is. Definition. A sublattice L is called a frame if the following distributivity law holds. So the distributivity law say that if you take the infimum, so I'm going to use the infimum, okay? So I gave you an example of a frame. You take the lattice of open subset of a topological space. It's important also to define what is a morphism of frame because that's going to make precise the operation that we are looking at when we look at the graphic. So the morphism should preserve the basic operations. So the map between two frames is a morphism. A frame. If so, there are two conditions. It should preserve suprema. And second, finite infima. So I'm writing one for the top element. Every frame has a top element, and the top element is actually just can be defined to be the infimum of the empty subset formally, or the supremum of everything, but it's better to define it as the infimum of the empty subset. So this is, so an example is that if you have a continuous map between topological spaces, then you get an inverse image map. You can, the inverse image of an open set is open, so you get an inverse image map from the open set of Y to the open set of X. Now, OX and OY are friends, and this map is a morphism of a frame. Okay, so we have a category which we could call the category of friends. And this is the category that people doing formal topology are studying. The category of frames and morphism of frames. Well, people doing formal topology, they study this category a lot, but they actually study the opposite category. So the opposite category, every category, this is a phenomenon which is really very important in category theory. Given a category, you can consider its opposite as a category. Every category has an opposite, just by reverting the directions of the arrow. And this is a very important phenomenon in category theory and mathematics. And so when we compare topological space to frame, we see that the direction of the morphisms are reverted. Given a map from X to Y, we get morphisms of frame in the opposite direction. So if I want to consider that a frame is a topological space, I should reverse the direction the other way. So a locale, the category of locale, is defined to be the opposite of the category of frames. So what does it mean? That it means that we formally sort of revert the arrows of the category of frames, and the new objects are called locale. So a locale is just a frame that view it in the opposite category of the category of frames. So there is there are two categories: locale, frames. There are two categories, and there is a duality between the two. actually, this the category on the left is a sort of mirror image of the category on the right. So this is actually just a way of looking at this category by looking upside down. But it's good to look at this category a little bit as if it were independent of that, and that there is a duality between the two things. So given a locale is the dual of a frame. And let's call it X, right? And when you write this, where A is a frame, you would like to think of A as the open set of X. So this notation could be reverted, and writing is just a notation. You pretend that A is the open set of X because you would like to think that the frame is some kind of topological space. And it's true. I mean, most frames are actually a frame of open set of a topological space, but there are frames that do not come from a topological space. Okay, so you have somehow expanded the category of topological space by the category of locale. And similarly, so what is a map between two locales? Okay, I have two locales. What is a map between the two? Okay, by definition, this is a morphism of frame from OY to OX. By definition, F is just a morphism of frame from OY to OX. Okay, so people doing formal topology are in a curious situation. They study locale, they are interested in the category of locales, right? But somehow each time they want to prove something, they move here and they prove something here. Okay? They think geometrically here, see, visually we see the locale. We think of a locale as some kind of space, you know. Okay? But if you want to prove something, you have to go back to the constructions of this locale as a frame and prove something here. Okay? So this is geometry here. This is an instance of a duality between geometry and algebra. There are many instances of this duality between geometry and algebra, and this is a sort of contravariant duality. We'll see other examples. Now, one possibility, when you see a situation like this, you say, oh my God, do I really need the category of frames, okay? I'm going to take a shortcut. I will say, I will call a frame, I will call it a locale. Let's not bother call it a frame. I'm interested in the dual locale. So I will call a frame a locale. Okay. Then I have to say what is a map from this locale to this locale. Oh, it's a map in the other direction. Between what? Are we here? Are we there? It's become very confusing. Okay? Of course, the experts are not confused. The experts, they know perfectly well what they do, and they are never confused. And it's a bit of the problem with mathematics. In every field, there is some kind of fault knowledge, which the experts share, and that makes many things very obvious. But if you come from the outside, you don't have this fault knowledge, and things are very confusing, or very mysterious, or impenetrable, and etc. So I think it's one of our okay, I will not say more about this. Okay, There is an important thing about the category of frames, which I didn't say. I said it's algebra. There's an analogy between frames and the theory of frames and commutative rings. So if you have the category, you have the notions of commutative rings. The notions of commutative rings is based on two operations: addition, additive operation, and multiplicative operation. X plus y, okay, and x times y, and the unit. And the theory of frames is also based on two operations. Well, suprema. You should regard the supremum in a frame as somehow the addition, and the infimum, the finite infimum, as the multiplication. And this analogy is very powerful because you can develop the theory of frames on the model of the theory of commutative rings. For example, an important constructions in the theory of commutative ring are polynomial rings. Okay, so you can construct polynomial rings over a certain number of variables. Okay. And you do it in two steps. You first construct the multiplicative monoid of monomials, and then you take linear combinations of that. Okay? And you're done. You have constructed the free polynomial ring of variables. The same thing with frames. Okay? If you have a poset P, it can be always be embedded in a certain frame freely generated by P. I'm writing B here because here the rings of integers is the sort of the smallest ring, possible ring, in the sense it's the initial object of the category of commutative rings. And in the category of frame, there is the smallest frame also. It is the Boolean algebra 0,1, or the poset 0,1. It's the smallest. And the construction of the free frame generated by a poset P is very much like this construction. You do it in two steps, and the two theories can be developed in parallel. There is a theory of ideals here. There is a notion of ideal in this case. It's called a kernel, and the theories are very similar. And there is a huge parallel between the two things. Now look, there is a huge parallel between the theory of frames and the theory of commutative ring. This is the theory, this is algebra here. Here we are talking about algebra. This is algebra, okay? This is entirely algebra. And so by looking at algebra opposite, okay, by reverting the arrows, we get into the geometry, you see? Okay, so this is something I would like to emphasize also for toposes. Okay. Oh, there's one more aspect of the theory of frames, is the connection between logic. So every frame has the structure of a Heyting algebra. I recall that the Heyting algebra H has an infimum operation, supremum operations, and an implication. It has essentially three operations, and the implication, if H is a frame, if A is a frame, then X implies Y, and denote it like this, okay, logical. Okay. X implies Y can be defined to be the supremum of all Z such that Z intersection X is smaller than Y. And with this operation that can be defined on any frame, you get the structure of a Hutting algebra. And Hutting algebra, of course, was invented by Hutting as a formalization of propositional intuitionistic logic. So you have a model of propositional intuitionistic logic from any frame. Okay, so let's look at this, what happened. Maybe I should take oh, this is okay. So we have the notions of locale, which is dual to the notions of frame. And from a frame, you can get a Hutting algebra. The theory of Hutting algebra and the theory of frames are very different for the following reason. See, a morphism of Hutting algebra should be a map that preserves the operations. And the operations there are three of them: conjunction, disjunction, and implication. It's not true. If you take a morphisms of frame, it happens that a morphisms of frame is not the morphisms of Hutting algebra in general. So these objects are different, and maybe we should regard the implication on the frame that I have defined here. We should regard the implication here as a superstructure. In the same sense that the infima on the frame is a superstructure. The infima. It's part of the superstructure of the frame. Okay, now I'm going to write the corresponding things here. Topos, Rosenthal topos, are like the two locales. Remember, this line is about zero topos. And now I'm talking about one-topos, which are Grothendieck topos. Okay. So the locales are like at this level, they are just the Grothendieck topos. And here, they are the elementary topos. Because the operations on the elementary topos are obtained exactly in the same way. It's a kind of superstructure. The structure of an elementary topos is a superstructure that exists on any Grothendieck topos in the same way as the implication exists on any frame. Okay, so I will discuss that in a moment, but then there will be a problem. What should we put here? How is it that this is missing? I mean, mathematicians have developed the theory of locales and frame with two distinct names for a very good reason. Is that the theory of frame is algebraic. It's a theory of an algebraic object. Okay? And locale is a sort of obtained by duality. Now, I believe that the reason it is missing is that Grothendieck actually, what he described it was something here. But he wanted to see it geometrically. He wanted to say, oh, he said, oh, I have described a new form of space. I would call it a topos. So he didn't bother to give a name to the algebraic side because he immediately jumped to the geometric side. And this is making the topos theory kind of a bit schizophrenic since the beginning, because you don't have a name for that. I will suggest something. I will suggest to call that oh my God. A protos. Protos because first. Okay, so we have topos, and really what Grothendieck did was to, I will describe what is a topos by axioms. And we will define the category of protoi. Then the opposite category will be the category of topos. Okay? Okay, but then, how should we call that? If this is called protos, what should we call that? Okay. Okay. So I suggest to call that a logos. Because it has something to do with logic. And in some sense, this could have, a name like this should have been given by de Laurier from the start. And I heard a story from Edouard de Dubuc, who was a student of Saunders MacLean at the end of the 60s, that Grothendieck visited Saunders around 1969, the notions of elementary topos from Laurier and Tierney had been out. Saunders knew about it, so Saunders introduced this notion to Grothendieck, this notions of elementary topos, and Grothendieck was liked the notion. There's one thing he didn't like, that is the name. You see, he thought that this was not generalized topological space. Okay. Of course, each time you have topos or protos, you do have an elementary topos or protos. You do have, okay. But there are examples of elementary topos who are not topological at all. They are not, do not come effective, some so-called effective topos, has nothing to do with topology. But it is an elementary topos. So it's almost like proof that the notion is divorced from, although, okay. So let me define now what is a protos. Oh, by the way, I'm suggesting this terminology for the purpose of this talk. I will see in my paper if I keep the same terminology. And I do not have the power to tell people that they should change the terminology. I know that if you are used to terminology, using it for years, you just don't want to change. It's kind of difficult to start. It seems bizarre to start calling an elementary topos or logos and etc. But for the purpose of making things straight, in the sense that to sort of understand what's happening in this subject, at least these words are useful, okay, to make some distinction. So, the protos. So, soup lattices are analog to something called presentable categories. And frames will be analog, maybe without S, to what I will call data protos. But before defining the notions of protos, I need to say something about presentable categories. Because here, before defining the notions of frame, I started by describing what is a soup lattice. So there is this the analog of what is it. Okay, so the definition. A category let's say E is presentable if it is co-complete now co-complete means that every diagram in E has a colimit. The idea of a colimit of a diagram is like the idea of a supremum of a family of elements. So I want to treat colimit operation as the supremum in soup lattices. Now, if it is co-complete and generated by a set of small objects, I do not have the time to define what is a small object, but every object that you encounter in mathematics, almost every object is small. And generated means that starting from a set of small objects and taking colimit operation, you can get everything. Okay? So this is, the definition is a bit vague. But that's the idea of what the presentable category is. And a functor, a morphism of presentable category is a functor. So a functor is a morphism of presentable categories if it preserves colimit. So colimits, I said, are like suprema. So to say that the functor preserves colimits is like saying that a map between soup lattices that preserves suprema. Okay. A functor that preserves colimits is also said to be co-continuous. Okay. So I hope you are familiar with the notions of colimits and limits and things of this sort. I know very good mathematicians who sort of understand category theory, but they can never figure out which one is which one between limits and coordinates. It's kind of amazing. I mean, yeah, supremum and infimum is okay, but colimits and limits, it is something which, it could be, you know, that colimits looks like cohomology, and maybe cohomology looks to be contravariant, and then you get completely confused. I mean, I'm talking about mathematicians whom I have great respect. I'm very good mathematician, much better than I am. They always need to be recalled which one is which one if they read a text like that. Okay, so what is now definition? Category E is a protos. If, okay, so there will be various conditions. One, E is presentable. So it means that there are plenty of coordinates. I should say that the presentable category has also limits. It's like a suit lattice, as in phyla. Well, presentable category, you can show that it has limits also. So, and second, the pullback, the base change functor, f of the star from E over B to E over A, preserve coordinates. For every map. And third, the functor is the sub-object functor, sub, which is a contravariant functor to set that takes to push out to pull back. So sub A is the set of sub-object of it. So a sub-object of A is defined by a monomorphism with target A in the category. There is a monomorphism. And you can put back a monomorphism and along the map, and it's again a monomorphism. So if you have a map from A to B, you will be able to put back a monomorphism, and you get a contravariant functor, which I call the sub-object functor. Takes push out to put back. Okay, that's the three axioms. The most mysterious one is possibly the third one. The second one is a distributivity law, because it's like the distributivity law of infimum under supremum. That's because what does it say is that if you have a diagram D indexed by the small category I into E over B. From the diagram, you can take its colimit, which somehow is an object of E over B. And then you can pull it back. So you have DI over B. You have the map F from A to B. And you have a pullback function F of DI. And what you're saying is that colimit of the pullback diagram is the pullback of the colimit. So you're saying that the colimit of the F minus 1 of DI, F star of DI, the colimit, the colimit, at the supremum, is the same thing as the pullback of the colimit. Now this can be also written in terms of taking Cartesian Faber product with A. So this is saying that A cross over B of DI and colimit of that are the same things as A cross the colimit of the DI. And now we recognize that this is a symmetry Taylor between taking pullback and colimit. So this is very like as in the definitions of this term. Okay, the axiom number 3, which should be called the descent axiom for monomorphism, because it is a special case of descent axiom which was given by Charles Reck for the notions of infinity topos, but it is restricted to monomorphism. The reason, there are many ways to describe what a protos is. I could have used a zero axiom, for example, this axiom of zero. But I decided to use these axioms because they are clearly all given in terms of colimits and finite limits. They are axioms about, if you compute with colimits and finite limits, you will use a certain number of commutation rule, like the distributivity, for example. And these axioms are really about these two operations. They involve only finite limits and colimits. Now,
André, does the second axiom have an analogy in frames?
I'm sorry?
The second axiom,
Yes?
does it have an analogy in frames? What is the...
No, that's no. It's a new axiom that sort of pops out.
The second one.
The third one.
Yeah, well, the second one is what you just said.
Oh, the second one.
It's
The second one, yes.
distributivity of mean over
Same
joint.
way distributed.
Yes, the second one is distributivity, but this one is new. Yeah, it's new. There's the notions of n topos, and for the notions of n topos, you only have to replace 3 by something else, which is of the same type. Instead of taking sub-objects, we describe something more involved, but this is the same type. So the notions of infinity topos is exactly the same, except that instead of using monomorphism, you take all morphism. Okay, this is the same axiom in the case of infinity topos, except that you use all morphism. But with the but you have to replace set by the category of space and etc. There are a lot of.
Maybe this is a good time to give you a 5-minute warning.
Okay. What time is it now?
Well, it's about 5 minutes or at most 10 until the end of the talk.
At 5, I mean?
It's 5:37. So we want to go until 5:45.
Okay,
About
let's see. I started at 4.
4:30.
At 4:30, okay. Now it's a bit more than 1 hour.
A bit more than that.
Okay, thank you. Yes, I will take,
10 minutes.
yes.
So, what is an elementary topos now? What happened is that from 2 implies that the functors f of a star has a right argument. That's because any functors preserving colimits between presentable categories has a right adjoint. And this right adjoint, of course, by Grudenzik it is denoted F lower star. And type theorists would denote it pi product along F also. Maybe Lavire also, I think, introduced this notation, product along F. So this is one of the basic operations of type theory, to take the product of family of types over A along a map from A to B, and you get the families of types over B. Okay? And 3 implies that the functor sub is representable. Which means that you can find an object by an object called omega, and so that the sub-object of A are in natural bijection with the map from A to omega. Okay. Now, these 2 observations are exactly what in elementary topos is the notions of elementary topos is based. Category with finite limits is said to be in elementary topos. If the pullback functors have a right adjoint and the functor of sub is representable. So we see that every protos is a logos. And the fantastic discovery of Lavire and Tierney is that these notions of elementary topos or logos is really a set theory, and it's realistic set theory. To every protos, you can associate a set theory, a intuitionistic set theory, a model in some sense of intuitionistic set theory. Now the chain of things coming from 0 topos, 1 topos, 2 topos, etc. 0 topos, 1 topos, and infinity topos comes with the underlying structure of a 0 topos is a partially ordered set, so it's a prose set. The underlying structure of a 1 topos is a category,
and the underlying structure of infinity topos is what we have been called an infinity one category. And so the passage from one-topos to infinity topos essentially consists in replacing category theory by the theory of infinity one categories. I think it's a kind of surprising fact. I find it very surprising that the whole of category theory can be extended to infinity one categories. Take a book of category theory, you can find an extension of the result, the notions in there, in infinity category theory. There is, the extension is not always totally obvious, but somehow it works. It's an empirical fact. I mean, things could have been different. I mean, but it happens that people have introduced the notions of infinity one category, and then observe that there is such an extension. And if you, in this extension, the notions of one-topos extend naturally to the notions of infinity topos. And this is the second mutations of topos theory. Okay, I guess I'm getting maybe close to the end. I should stop here. Thank you.
There must be some questions, comments? No?
So is the opposite of the category of protoses equivalent to the category of protoses?
Category of processes?
Protos, the category of
Oh,
protos.
yes, right.
Is the opposite the category of
Yeah,
topos?
the category of protos, the morphisms of protos, is a functor that preserve co-limits and finite limits. Okay?
That's pretty good.
It's preserve the basic operations which are co-limits, like suprema, and finite limits. Okay? This happens to be a two category because you can look at natural transformation between two functors. Okay? There's an extra structure, it's a two category. And so you have the category, the two category of protos, of toy. Okay, and if you take the opposite of it, that would be the category of topos. Okay. So a topos is defined formally exactly like a locale is defined formally from a frame. This is defined from a protos. Okay. And it happens that the theory of protoi is very much like the theory of commutative rings. And you have an incredible correspondence. You can define free, construct explicitly the free protos generated by a small category. You can also describe the equivalent of ideals, and etc. And there is an incredible, very useful. It's very useful, this analogy. I think that Mathieu will say more about that tomorrow in your talk at
1 o'clock. 1 o'clock in
At
Baker
1 o'clock.
Hall, 150.
Okay.
The question is,
So maybe you just said this, but I wasn't sure. So you have the notion of topos as you define it here, and then you have the the category of topos as you define it here.
Yes.
You have the category of broken deep topoi and geometric morphisms as traditionally conceived.
That's equivalent.
It's equivalent.
That's equivalent.
As two
Yeah.
categories.
There is some kind of difference, but which are not essential difference, is that in the definitions of probability, a morphism is like a functor like this, that preserves colimits and finite limits, but he asks that the functor has a right adjoint. Instead of asking that the functor preserve colimits, he asks that the functor has a right adjoint, which we call the Dirac image functor. And, but this condition is equivalent. I mean, the functor has, between presentable category, has the right adjoint if and only if it preserves colimits. So the right adjoint is like a superstructure again that comes. Okay, that's very useful. The right adjoint is very useful. But I would say it's not part of the basic structure of the category of protoi or topos.
Any questions? Which one?
I just wanted to check my understanding on something. Your third axiom, so you said this is a special case of something that you see in higher toposes, where instead of just monos, we look at all maps. Is that the only part we have to change, or do we also have to say, like, for the push-out, the pullback part, does that have to change at all in the higher case?
No, that's essentially it. You take all maps, but you have to be, of course, have some care in describing what it means, that it takes push out to pull back. But this condition 3 is what we call the descent principle of Charles Reck. See, Charles Reck invented the notions of infinite topos when he observed that this descent property, which is only true for mono in the case of ordinary topos, is actually true for every map in the homotopy context. It was really a great insight that you could create a new notions of topos using this condition 3. Yeah.
Which functor would still be the sub-object functor?
My ears are not good, so maybe if you can...
What is the functor in the higher case, the infinity topos say? Instead of the sub-object functor, we have to replace that with a different functor.
Yes, that's true.
And which one is it?
Yes, right. So instead of taking sub A, the sub-object of an object A are contained in E over A.
Yeah.
Yeah, because they are maps, okay? So you have to replace this by cat. Well, actually, infinity one categories, okay? So this is why it's a little bit, okay, infinity categories. And the functor takes an object in the protos and send it to E over A. Okay? And what you say is that it takes push out to pull back. This axiom is just an amazing axiom. This descent axiom, it's an amazing axiom. It's kind of the basic axiom that has been used by people doing multiple type theory, for example, for proving the Blaker's-Massey theorem. A new proof, giving a new proof of Blaker's Massey theorem in multiple theory. You have this descent principle, which is a key argument in the proof. And it was also a key argument in the generalization obtained by Michael with Eric Fenster, Mathieu, and George Biederman, and myself. These axioms are really very powerful tools. They really, if you want to prove something very basic and important, non-trivial in multiple theory, you may have to use these descent axioms, and only them. They are almost like necessary and sufficient. Everything turns around these axioms. They're really. The subject is kind of amazing.
I'll ask a question. In the one-topos case, the existence of this third condition here led to the representability of the functor.
Yes.
In the higher topos case, so, which is a superstructure. It's part of the
superstructure.
elementary
Yes.
topos, but not part of the protos.
Yes.
In the infinity case,
Oh,
it also leads to a superstructure in the infinity protos. Do you call it that? Do you call it an infinity protos, or?
yes, we can call it infinity.
Well, if you want to, we don't have to, but. And so there's a corresponding superstructure in the
Yes.
infinity protos.
Oh, I'm very happy that you're mentioning this.
I
Maybe
wonder
you
what
want to
this
say,
is.
please.
No, you say, please. It's your talk.
Well, of course, here is just the right-hand one. It is the
Yes.
product. That in type theory.
That's just the
In
part.
multiple type theory, you have the product of types and types, etc.
Yeah.
But here, what this larger functor is represented by what type theorists have called a universe. And Martin Love had a notion of universe in type theory, and the fact that it is representing this functor is what Vladimir Voyevitsky discovered, is that one should put an axiom about the universe that it represents this functor. That's the famous univalence axiom of Voyevitsky. So, in the context of infinity protos, or logos actually,
Now you need a new name, yeah?
omega is replaced by a universe. Okay. Yeah.
Yeah, it's quite beautiful. Quite a beautiful idea.
Oh yes, it's just amazing. I mean, you know, I'm very familiar with topos theory since a long time, and I have been doing homotopy theory since quite a long time too, and I have not connected the two things. I mean, you see the two things, the topos theory and homotopy theory, are very closely connected in a very nice way. But in my professional life, I was doing topos theory and homotopy theory. So I needed people like Steve and Voyevitsky to orient my sight in the right direction. So I'm very surprised that these things exist, that is work. And this is why I tend to say that we live in the best possible world, at least mathematically.
Please join us upstairs in Baker Hall 135 for a